Okay, so welcome to this final video on Unit 2 Waves ISP. It's the final task. Task 5 is the one we're looking at today. Just to give you a warning that during this video at some point a pop-up will appear for one of the previous videos I've made asking me if I wish to view it, because I'm just converting that in the background right now. So apologies for that pop-up in advance. So task 5, what we're looking at is we're looking at the process of polarization, describing the electromagnetic spectrum, and also the idea of Doppler shift and ultrasound. So they're pretty straightforward ideas. The only one you haven't come across before is polarization. The other three ideas in there you'll all come across at GCSE. What I'll say is there isn't much on the electromagnetic spectrum, but what you need to do is make sure you can identify regions of the electromagnetic spectrum by frequency, by wavelength, essentially. So make sure you can do that. So apologies for my webcam fading in and out as well. I'll put my pin on there to make sure it doesn't keep happening. Let's get straight on with the explaining everything tasks. So, first thing is describe how light can become polarized. So remember, light oscillates in two dimensions. Sorry, let's get this webcam set up. Okay, so in two planes, I should say. So you could have oscillations taking place like this. You could have oscillations taking place like this as well. Okay. So if you were to look at that head on, okay, you'd end up with oscillations taking place like this. Well, actually, it's not just two planes; it oscillates in many planes like this. Okay. So when we draw this, we draw the two planes in there, but it can oscillate in any direction. If that wave then went through a filter, a polarizing filter that only allowed oscillations in one direction, it became plane polarized. It would become plane polarized as it came out. So remember, you've got to draw your arrowheads on here. This is what we call unpolarized light. This is what we call polarized light. So unpolarized, polarized. Unpolarized, polarized. Okay, so upon reflection, light becomes polarized. That's key. So if this light was to reflect off, say, the surface of water in an ocean, it would come back polarized like such. Okay, so that's how light can become polarized in two ways. Number one, through a polarized filter, and number two, by reflecting off something like the ocean. So we need to describe an experiment to test how much sugar solution rotates the plane of polarization. So remember, this isn't just sugar solution that actually could do this. Okay. You can actually do this with drugs in certain solutions as well, so this can be used for the idea of drug testing. So let's build on what we've got here. So we've got light, it goes through a polarized filter, it's plane polarized. If we then put it through a sugar solution, what sugar solution does, because the molecules in there, they rotate this angle of polarization. So if you figured out where it actually was, it'd end up in a specific place afterwards, and you could figure out how much has actually changed the angle of rotation, and therefore or figure out the concentration of the sugar solution. Different concs or different concentrations mean you have different angles of polarization. So different rotations of angles of polarization. So you can't read any of that, but all I've written is different concentrations lead to different rotations of angles of polarization. So if you have a different sugar solution in here, it leads to a different angle over here. So how are you going to measure that angle? We need a protractor to do that, and obviously you need a light source to allow all this to happen as well. So the piece of equipment that you have is called a polarimeter. I'm sure if we have a quick look on Google, we can find a decent picture of a polarimeter. Polarimeter, right. Images. Oh, there we go. I can see one there actually. Oh, here you go. This is very, very good. This shows it very clearly actually. Okay, so just one picture. Yeah, image new tab. That would be the best way to do it. And let's zoom in on this. Okay. Oops. There we go. So you have light that's coming in. It's unpolarized. Goes through a polarizer or polarized filter. It becomes polarized. Goes through a sugar solution. Okay, that sugar solution rotates the angle of polarization. Okay, so we need to rotate this for us to actually be able to see light. If we didn't rotate this to see the light, we wouldn't be able to see anything. So you rotate it to see light. Well, this is quite interesting, because do you want it so that you actually get light through there, or do you want it so you don't get light through there? Sometimes it's easier if you don't get light, because seeing the absence of light is easier than seeing, well, is it at its brightest point or not. So if you rotate this originally when there's no sugar solution in there to the point where it's completely dark, and then you try to rotate it again to where it gets completely dark and measure the angle that's actually changed between the two, you could figure out the angle of polarization. Nice and straightforward. Right, Doppler effect. Very straightforward Doppler effect. Definition, word for word. the observable change in frequency. So it's the observed change in frequency, sorry. Straight away I had a mistake there. The observed change in frequency or wavelength due to the relative motion. Actually, let's make this big. Relative motion of a source compared to an observer. Observer. Okay, compared to an observer. So the idea is an observed change in frequency or wavelength. It's not an actual change. Okay, it's an observed change. It's due to the relative motion. That's what it's due to. Okay, so if I show you an image of this, I know it's a very good one on Google. It's normal side. Okay, you can see it over here. This is the one that I like to use in class. I should just click a few images there, shouldn't I? Silly me. Scroll down. There we go. I did this last time, so there we go. Right, so if you had the idea that we've got a source of sound here that's moving, you've got two observers, and they're experiencing a change in the frequency. They see a small frequency, small wavelength, see high frequency. This one experiences a long wavelength, therefore a low frequency. Well, has the frequency or the wavelength actually changed? Well, no, it hasn't. Okay, the only thing that's changed is relative motion between these people and the car. So they're not moving, the car is moving either towards them or away from them, and therefore they have a change in frequency or wavelength. If they were running at the same speed as the car, they wouldn't observe a change. So remember, if these guys were running as quick as this one over here, they would actually pick these waves up as quickly as they're released from here, so there'd be no observable change. And it's the same idea with this guy here. Right, nice and straightforward. Let's delete that before I save it in this document by accident. Okay, so describe pulse echo techniques. So for pulse echo techniques, again, why don't I find a lovely picture of this on YouTube? Pulse echo technique. There you go, first one. Okay, here we go. Yeah, this is a good one. Yeah, okay. I'll make sure I learn and just click on view images time. This clearly shows what's going on. Okay, so say you've got a device that causes a wave to be produced, i.e. an ultrasound wave. Okay, so remember ultrasound above 20,000 hertz. Okay, the wave would come down and it reflects off the surface. Okay, so you'd have it go back to the receiver. Okay, now if you knew the time it takes to go from there and get back, remember, if you want to figure out how far away this impurity is over here, you need to half the time, because it takes twice as long to go there and back, so you need to half it to figure out the distance that is away from there. And it's straightforward as speed equals distance over time. In terms of what you actually end up with on a graph, let's type graph after that. There's a lovely question on this coming up in the ISP, so we can focus on it then. But you'd end up with, maybe this is pretty good. No, not the best. Maybe something like this. Yes, you'd end up with spikes in the graph wherever the reflection took place. Okay, so actually this one here is pretty good. Okay, so you can see there's two cracks. Okay, so there's two defects in here. Okay, so there's the noise at the start that you get from the first reflection, but then you get a reflection from the first defect, and then you get a reflection off the back wall as well there. Because this defect's in the shadow of this defect here, it wouldn't actually get picked up unless diffraction took place. Okay, so you get reflection off the back wall there as well, and that's what this is here. So you wouldn't pick that defect up because it's in the shadow of this one. So unless you've got diffraction taking place around the edge of that, you wouldn't pick that one up. Okay, so that's the end of the explaining everything. Let's get stuck into some questions on this now. Let's get rid of all these things that I've typed and any errors and made this document. 26, if I remember correctly, is where we're starting. Yep, here we go. So, first question. Ultrasound images of the body are a useful diagnostic tool. So we've got a diagram here that is not drawn to scale, but they've given us some distances here which help. So calculate the time interval between sending out a single pulse and receiving its echo from interface B. The speed of ultrasound in the abdominal wall is 1500 meters per second. So we've got the speed, 1500. Okay, we've got the distance, so it's there and back again. Sound like something from The Hobbit. That's 2 centimeters times by 2, so that's 4 centimeters. but hold on, that's 0.04 meters. Okay, so now we want the time. So essentially it's speed is equal to distance over time. Time is equal to distance over speed. Okay, so it's going to be a very short amount of time, so you end up with 0.04 divided by 15,000. So there's my numbers that I wrote down just up there. 0.04 divided by 15,000 equals, right, so it's about 2.6 reoccurring times 10 to the minus 5. Okay, so it's going to be a 2.6 reoccurring times 10 to the minus 5. Yeah, I don't know why I'm thinking 26 there. Let's have a look, see what it says. Okay, yeah, so 2.7 times 10 to the minus 5. There we go. Nice straightforward question. Next. So a very small amount of time. The time between the pulses is 2,000 microseconds, that's times 10 to the minus 6. And they want to know what the frequency is. So we've got the time period, we want to know the frequency. So it's 1 divided by the time period. Okay, so you can see I've done that there. 1 divided by 200 times 10 to the minus 6. So equals 5,000. The frequency of this was 5,000. But the frequency and the speed, so we can figure out the wavelength if we wanted to. Okay. Time interval before the echo returns from the interface is 250 microseconds. All right, so that's quite close. Well, that is actually longer than the time between pulses. Suggest why this time interval will make the reflections indeed difficult to interpret and what could be done to overcome this problem. Okay, so it would be difficult to interpret because you're going to send a wave out that's going to interfere with the wave that's coming back before the wave actually returns. So there's your problem. So to overcome this, you need to increase the time between pulses. There's your idea. Okay, so the problem is you're going to get interference. State one reason why ultrasound rather than X-ray is now used to scan expectant mothers. We know that X-rays are ionizing, ultrasound is not. So ionization can cause tumours and damage and mutations to this baby. That's still in a lot of mitosis taking place, and there's a lot of growth. So we don't want any mutations to take place there. However, ultrasound, non-ionizing radiation, no issues whatsoever. So ultrasound, non-ionizing, X-rays, ionizing. Okay, ultrasound is also used to measure blood flow in the body. It uses a Doppler shift of reflected pulse to measure the speed of blood through the arteries of the body. Describe the principle of this method and how it can be used to determine the speed of blood. So remember this idea, the whole idea of the Doppler effect is if there's, so state the Doppler effect, an observable change in frequency occurs due to the relative motion. So remember, the greater the change in frequency, the greater the difference in velocity. So from that we can figure out the speed of the blood. Right, let's have a look and see what actually happens. So remember, we're looking at the change in frequency compared to the change in speed. Alright, let's see what they've said. Oops, oh, there we go. No, I don't want to view that right now. I did warn that was going to happen. There we go. Right, okay, so time for the pulse to return is greater than pulse interval, so all reflections need to reach transducer before the next one. So this will produce an inaccurate image, in other words, the idea of interference. We need to decrease the frequency of the ultrasound. So that's one thing you can do. You can take a decrease the frequency of the ultrasound. Alright, so if you're decreasing the frequency, remember you're changing that time period. It's the same idea. You could talk about frequency or time period. X-rays causing damage, done that already. Okay, so logical sequence in this. Doppler shift, definition. Cool. You need to send waves continuously, so anything I didn't really mention. I also didn't mention the idea of two transducers required, so one to receive and one to actually give out the wave. And we're looking at the fact that the frequency is directly related to the speed of blood. So these are the 2 points that are crucial that I didn't say. Sorry about that. So you need to send out waves continuously so you can continuously monitor what's taking place. And also you need to have two transducers, one to give out the wave and one to constantly receive this wave. Okay, so what have we got left? 27 to 32. So 27, explain with the diagrams or transverse waves can be polarized but longitudinal waves cannot. So you need to draw what a transverse wave looks like, draw what a longitudinal wave looks like. I'm not going to do that now, we've done that in a previous ISP. Okay, so remember one has, so transverse waves have particle motions at right angles to wave motion, and longitudinal waves have particle motions parallel to wave motion. So remember, longitudinal waves cannot be polarized. Essentially, they're already polarized. They're only oscillating in one plane, while transverse waves can be polarized because they oscillate in many planes. Okay. So describe with the aid of diagram how you could demonstrate light can be polarized. So we've done that already with the idea of two Polaroid filters, and the fact if you rotate it. So if you go back to this over here, so if if you rotate one polaroid filter, put another polaroid filter beyond that, okay, you wouldn't get anything in that polaroid filter because of the fact that it's only oscillating one direction, so it won't be picked up here. But remember, if you rotated that through 360 degrees, twice you get maximum brightness, and twice you'd get complete darkness as well. So that proves that light can be polarized. That's the idea there. 28. So draw label diagrams to show polarized and unpolarized light. We know that. Polarized and polarized light. Explain how an astronomer's telescope could be adapted to overcome the problem of bright moonlight. So again, you're thinking about using the idea of a polaroid filter to reduce glare, because remember, it's reflected light, so you want to remove the reflections that you're getting. Some of the reflections you're getting that cause glare, so you can do that by using the polaroid filter and changing the angular polarization and rotating the filter to match the angular polarization. So 27. Okay, transverse waves, exactly what we spoke about there. Yeah, exactly what we said there about polarization. So limiting the oscillations of waves. So essentially, you cannot have that with longitudinal waves. Next, you've got a light source, two pieces of polaroid paper, exactly what we said. Okay, so you need to rotate it, the intensity varies, as we said. There's our one for 28 in terms of our two diagrams. So you fit to polarize the filter on the telescope, 90 degrees polarization direction to block the moonlight. Okay, so you need to rotate it until it cuts out the moonlight, essentially. Okay. So 29. Oops. Okay, so we're talking about the Raman effect. It's nothing to do with noodles before anyone thinks that. This Raman with noodles is EN at the end. This is AN at the end. Raman effect. So, Raman effect can be used to identify the chemical composition of solid materials in non-destructive manners. In other words, to identify things like fake diamonds without breaking them apart. So, laser light is shone and the light is then scattered. Scattered light would be plain polarized, right? So, there's our piece of knowledge we're using, plain polarized. And it will have been frequency shifted. Okay, so in other words, Doppler effect sort of ideas, undergone a frequency shift. This happens when the light interacts with vibrating atoms in the materials. Analysis of Raman frequency shift reveal the chemical position of the material. Brilliant. So what do we mean by plane polarized? It's a light that only oscillates in one plane. So the oscillations only take place in one plane. Similar light will have been frequency shifted by the moving atoms. Name the phenomenon which causes frequency shifting and briefly explain how it arises. Again, description Doppler effect. Okay, that's all thereafter for that. Okay, there's nothing trickier than that. Okay, that's all they're actually after. Okay, so oscillations are parallel to one direction, so they're only in one plane. Okay, Doppler effect, definition of Doppler effect, straightforward. Okay, all right. So next, I think yeah, final two bits of 29. Okay. So Raman frequency shifts are often measured in wave numbers. Wave number is 1 over the wavelength. So laser light of the wavelength, let's take this piece of paper over. Laser light of the wavelength is 1064 nanometers. Please don't ask me why they didn't do 1.064 micrometers, because they could have, I'm guessing they didn't want to do 3 decimal places. The scattered light has a wave number shift of plus 1300 centimeters, sorry, per centimeter. Show that the frequency of this scattered light is about 3 times 10 to the 14. This is tricky because we haven't really covered any of this in class, and that's because it's not really a specification point unless they give you information on it, which they have. Okay, so the wave number, let's just do a symbol like that for that wave number. That's supposed to be a hashtag, a generally poor hashtag. Is equal to 1 over wavelength. Why don't we use lambda for that? There we go. So we want to do 1 over wavelength. Sorry, no, we have the wave number, so we want the wavelength. So come on, better hashtag this time. There we go. Alright, so let's figure out what the wavelength actually is. So 1 divided by 1300 per centimeter, or let's do this in meters now. So let's convert that straight into meters. That's 1.3 per meter. Oh, sorry, no. 13 meters. So 1 divided by 13, essentially. Actually, I can't see the calculator. So 0.77. 0.077. So that's our wavelength, 0.077 meters. Okay, so that's 1, 2, 3. So it's 77 millimeters. Okay, that's our wavelength. Okay, so now when the laser says laser light, so we've got the speed. Okay, so we've got the speed that causes this shift in wavelength. So what it says is often, so frequency shift is often measured in wave numbers. So so this is essentially figuring out a frequency shift. So this is how much the frequency has shifted. Okay, so let's we know the speed of this is going to be 3 times 10 to the 8. So we want frequency. So frequency is speed over wavelength. The speed is going to be the speed of light. Let's replace that with c. So 3 exp 8 divided by 0. Divided by what is it? 3 exp 8 divided by 77 times 10 to the minus 3. Okay, so we've got a number here which hasn't shown up very well on my calculator. So I need to do a bit of movement. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 3.8 times 10 to the 9. Okay, but we've got to add that to our frequency from before. That's the point. So we're adding this to our frequency from before. So our frequency from before, we need to figure out from our wavelength from before. Well, I've got a long way about this. I could have just added my two frequencies together from before, and hopefully that would give me the correct answer. Okay, so I could have added my 77 millimeters to this wavelength over here. Okay, and put that into my frequency equation, and that should give me the correct frequency. So let's check to see that that would have been the correct technique, just to save us a bit of time, because I'm worried that this video is getting bigger and bigger in size. Where are we? Right, okay, so evidence of use of that. Okay, so laser wave number of 9,000. Okay, right, so there's the idea there of that change. So new wave number is that. So it's the idea of what you need to figure out what the laser wave number is. You need to add to it to figure out that one, which is what I said we need to do, or conversion to wavelength, which is the way we did it. Okay, so using that idea there, and then adding that to, so figuring out your new wavelength from that. I think I've got a couple of powers out with my wavelength. I think I've missed something out there. But yeah, so you just add them together, and therefore you do frequency equals speed over wavelength, like we said, and that tells you a new frequency. So the key point that I missed there was not adding the two wavelengths together, but I won't go through that. I'll just quickly go through the next couple of things, because I know I've got about 3 questions left still, and this video will get very large in size if I'm not careful. Okay, so next one. So essentially remember, add your wave numbers together before you do your frequency calculation. That's the only difference. A student correctly remarks that the frequency of laser light is changed and the energy must change. State the model of light that is being used by a student. Explain what must have happened to the vibrating atoms and time-reduced interaction. Okay, so E equals HF is the idea they're using. Essentially, they're using the particle model of light. Okay, so they're using the fact that E equals HF, particle model of light. So therefore, each photon of light must therefore have more energy. So each vibrating atom is going to vibrate faster at a higher frequency, therefore have more energy. Okay, let's have a look. Photon, so the energy of the atoms was to change. Okay, so they're vibrating faster. Okay, which means that the photon energy must have changed. Okay, so equals HF, and it's the particle model or the photon model or the quantum model. Any of those are fine. Okay, so next one we can just read it off the mark scheme already. It's asking what is polarization. So again, plane polarization, wave oscillations only occur on one plane. How to measure the angle of polarization, same as before. So this is to do with sugar solution. So I've been through that in terms of explaining everything. Polaroid filter both ends. Sugar, do it with no sugar solution first, then do it with sugar solution. Rotate, well, find a dark with no sugar solution, find the dark without sugar solution. Difference between the angles, boom, done. 4 marks. Now I went through that in class. I've demonstrated that to everybody with the piece of equipment. Okay, let's have a look at this graph question, because it will be something like this is asked quite often. So we need to plot these points onto the graph. Looks like there's potentially, it looks like there's potentially an anomaly there. So use the graph to. Actually, no, I don't think there is an anomaly. Let's have a look. No, there doesn't look like there's an anomaly there. Apologies for that. Okay, so use the graph to determine the concentration of an unknown sample. Rotation, which gives a rotation of 38. Okay, so you need to use 38 degrees, go across, figure out your unknown. Okay, so you can see it's going to be about 0.6. Okay, that's clearly not a very accurate way of doing it. Make sure you do it more accurately when you do it on the ISP. So, photography using polarizing filter over a camera lens. She notices the intensity of light received from the blue sky changes as she rotates the filter wide. What does it suggest about light from the sky? Okay, it's plane polarized potentially. Okay, so there could be some clouds that are causing plane polarization to take place. That's your idea there. Okay, so the fact that there must be plane polarization take place if it rotates as it comes from the sky. Explain the change in intensity as the filter is rotated. Okay, it's because the plane of polarization is matching up with the slit essentially in a Polaroid filter, and then it's not matching anymore. The use of Polaroid filters makes a blue sky appear darker, but the clouds remain bright, to suggest why there's little change in intensity of light from the clouds, because that's going to be unpolarized. Okay, that light is unpolarized. Astronomers notice the same effect with radio waves emitted by some galaxies. What does it suggest about the radio waves? Polarized light. Okay. State why radio waves should behave in the same way as light. Both of them are waves within the electromagnetic spectrum. Okay, let's look at 31 then. Transverse waves, electromagnetic waves is the idea. Okay, unpolarized, like we're saying, light from the clouds must be unpolarized. Radio waves must be polarized. Light is polarized, so over there. Change in intensity. It's the idea of rotating the filter. Straightforward. Okay, really, really nice question to get in the exam. Probably too nice. Too many people will get that. Okay, so we want a slightly trickier question if we want to be doing better than other people up and down the country. So 32. Okay, so this is the question I was talking about before. You can see two very nice lines on there in terms of reflections taking place. So speed of the ultrasound in the pipe. Okay, so we've been given the dimensions of this pipe. Okay, so when obstruction occurs in the pipe, an ultrasound probe connects to the oscilloscope. Okay, so you can use the oscilloscope to find out where the obstructions are. So figure 2, pulse A is an outgoing signal from the probe, and B is a reflected signal on the other side of the pipe. Okay, so they're saying calculate the speed of ultrasound in the pipe. So essentially what we need is we need to know distance and time. Okay, and from the ideas of distance and time we can figure out speed. Okay, so let's just check that we're using the right processes here. Okay, so the speed is 150 times 10 to the sorry, yes, that's right, the speed, no, sorry, the distance is 150 times 10 to the minus 3. Sorry, I was saying it right the first time. The speed is 150 times 10 to the minus 3. The distance is 132 times 10 to the minus 6. Therefore, you end up with the speed over it. Okay, so remember you've got to double you're doubling here because of the factors going there and back again. Let's get back to the question. Okay. Where are we? There we go. Okay, state one way in which the oscilloscope trace will change when the ultrasound probe is above the obstruction. Okay, so it's above the obstruction. Okay, in terms of this ultrasound pipe. Okay, when it's above it, over here. Okay, the trace will change in the sense of that there's two blips in there rather than just the one returning off the edge of the pipe. Okay, so there'll be another blip in there, another line going up because it's going to reflect off the obstruction and the end of the pipe. Okay. So that's how we can locate an obstruction in the pipe. Okay, after the obstruction has cleared, a Doppler ultrasound probe is used to measure the speed of the soup in the pipe. Describe the principle of this method. So that's exactly what we discussed before in terms of the artery, change in frequency. So you have to use two transducers, one to give out the sound, the wave, sorry, the ultrasound wave, one to receive it, and you're looking for a change in frequency, which is proportional to a change in speed. What must be measured to determine the speed of the soup? So in other words, the frequency or the wavelength must be measured. Someone suggests that it would be easier if the soup contained lumps like vegetables. Comment on the suggestion. Well, if it's got lumps in there, you can be able to measure the speed a lot easier because you've got objects where the reflections take place off. Okay, so lumps give larger reflections. Lumps travel slower. Okay, so frequency change is what you're actually after. A range of probes the soup is approaching. Okay, and then you've got to look at the idea of change in wavelength, change of speed. Brilliant. Okay, so that covers the so extra pulses was the other part that we said as well. So that covers ISP task 5 on waves, and that is the last ISP in waves. And if you've already covered the DC electricity one, that is your last ISP task for the two units. So if you completed both of these, good luck for your exam. Remember, you might want to go through these now without using the videos, so print off another version of these, blank version, go through them again, try to make sure you've understood everything that we've covered. So good luck, guys.